Hey there, and welcome. Today, we're going to dive into the invisible forces that literally build our entire world, chemical bonds. It's the fundamental glue that holds all matter together, and we're about to break down exactly how it all works. Have you ever stopped to wonder about that? I mean, why do different things behave in such completely different ways? A sprinkle of salt is this hard little crystal. A spoonful of sugar just poof, vanishes in your coffee. And a simple copper wire can power your entire home. On the surface, they seem totally unrelated, right? But they all share a common secret. And there it is. That's the key. The properties of every single thing you can touch, see, or taste are all decided by the chemical bonds between its atoms. So if you can understand these bonds, you can understand the material itself. It's that fundamental. Okay, so to really get to the bottom of this, we've got to start with the most basic question of all. Before we can understand how atoms connect, we first need to figure out why they even bother doing it in the first place. It all comes down to one thing: stability. Think of an atom like an onion. It's got layers, and these layers are called electron shells. Now, atoms are most happy or stable when their outermost shell is completely full of electrons. So bonding is just the strategy they use, gaining, losing, or sharing electrons with their neighbors, to fill up that outer layer and get to a really stable, low-energy state. So how exactly do they get to this stable state? Well, atoms basically have three main moves they can pull. They can give electrons away, they can share them, or they can kind of let them swim around freely in a big group. And these three strategies give us our three main types of chemical bonds. First up, we have the ionic bond. You can think of this one as the give-and-take bond. It happens when one atom completely hands over an electron to another. Now, once an atom gains or loses an electron, it's not neutral anymore. It becomes a charged particle we call an ion. This whole transfer creates one positive ion and one negative ion. And just like magnets, opposites attract powerfully. Okay, this slide's got a lot going on, but let's just zoom in on the diagram in the middle for magnesium oxide. You can see the magnesium atom on the left has 2 electrons in its outer shell. It doesn't want them, so it gives those 2 electrons over to the oxygen atom. Boom! Now magnesium has a positive charge and oxygen has a negative one. It's that powerful attraction between those opposite charges that, snap, locks them together. This is exactly what holds a salt crystal together. All right, next up, the covalent bond. Instead of a transfer, this is all about partnership. In this case, atoms actually share electrons to complete their outer shells. It's a total cooperative effort. The whole idea here is teamwork. Instead of one atom just taking electrons from another, 2 atoms share them. Both of their centers, their nuclei, are attracted to that same shared pair of electrons. And it's that mutual attraction that holds them together. This creates a neat, self-contained unit we call a molecule. Things like water, carbon dioxide, the sugar in your coffee, they're all molecules held together by these cooperative covalent bonds. And finally, we get to the really unique metallic bond. This is what's happening inside metals, like a copper wire. I want you to picture a grid of positive metal ions, just sitting there in what's basically a collective sea of electrons that have detached from their home atoms. These electrons are called delocalized, which is just a fancy way of saying they don't belong to any single atom and are totally free to just move throughout the entire structure. And that sea of electrons is the secret sauce behind all of a metal's famous properties. I mean, why does a copper wire conduct electricity so well? It's because that sea of free-flowing electrons can move easily, carrying an electric current with them. This unique structure also explains why metals are so strong and why they conduct heat like a champ. But that whole idea of sharing electrons we just talked about? Well, it gets a little more interesting. See, it's not always a perfect 50-50 split. Sometimes one atom pulls on those shared electrons a little bit harder than the other one. And this tiny little imbalance has massive consequences for the shapes and properties of molecules. The key concept we need to understand here is called electronegativity. It's basically a measure of how greedy an atom is for electrons when it's in a bond. You can seriously just think of it as a chemical tug-of-war over that shared pair of electrons. So let's look at how that tug-of-war plays out. Focus on that horizontal bar graph in the middle, the one labeled electronegativity difference. If the pull from both atoms is exactly the same, that's what you see on the far left, they share the electrons perfectly. That's a nonpolar bond. Now, as you move to the right, one atom starts pulling a little harder. You get unequal sharing, a polar bond, with tiny positive and negative ends.
And if the difference in strength is huge, all the way on the far right, the stronger atom just rips the electron away completely. And look at that, we're right back to an ionic bond. It's all just one continuous spectrum.
Okay, now it gets even cooler. All those pairs of electrons buzzing around in a molecule, the ones in the bonds and the spare ones, they're all negatively charged. And what do like charges do? They repel, so they are actively pushing each other as far apart as possible. And it's this repulsion that literally forces a molecule to bend and twist into its specific three-dimensional shape. So the big takeaway here is that a molecule's shape isn't random at all. It's totally predictable. A great way to think about it is like tying balloons together at their knots. If you tie two balloons, they're going to point in opposite directions, right? A straight line. That's a linear shape, just like CO2. If you tie four together, they'll naturally form this 3D pyramid shape called a tetrahedron, just like methane. The number of electron groups around that central atom dictates the entire geometry. It's that simple. All right, so far we've been talking about the really strong bonds within a single molecule. But what about the forces between separate individual molecules? These forces are much weaker, but they are just as important for understanding our world. And this chart shows us that there's a clear hierarchy of forces. Let's break it down into two main categories. First, you've got the super strong bonds holding the atoms together inside a molecule. Those are the ionic, covalent, and metallic bonds we've been talking about. But then, you've got these much weaker forces that cause whole, separate molecules to attract each other. These forces between molecules, or IMFs, come in a few flavors. The absolute weakest ones are kind of like fleeting little moments of static cling that exist between all molecules. Then there's a stronger type that exists between polar molecules. Remember those? The ones that act like tiny little magnets with permanent positive and negative ends? And then, the strongest of them all is a special, supercharged version of that magnetic attraction called a hydrogen bond. Okay, let's put it all together now. How do these bonds inside molecules and these forces between molecules combine to shape the world we actually live in? Well, there is no better example on planet Earth than water. This is the payoff slide, right here. This is where it all comes together. So look at a single water molecule, H2O. Because oxygen pulls on electrons way harder than hydrogen does, the bond inside the molecule is polar covalent. This makes the oxygen end a little bit negative and the hydrogen ends a little bit positive. And because of that, the whole molecule acts like a tiny magnet, forming these incredibly powerful hydrogen bonds that connect it to all the other water molecules floating around it. And this brilliant 1-2 punch is what gives water its superpowers. Those strong hydrogen bonds need a ton of energy to break, which gives water its ridiculously high boiling point. They also force the molecules to arrange into this rigid, open crystal structure when they freeze, which is why ice floats. This one single type of bond is responsible for, well, life as we know it. So from the salt on your table to the water in your glass, everything is governed by these basic rules of attraction and connection. The real question is, now that you're armed with this knowledge, what other mysteries in your daily life can you start to unlock?